Hello, welcome back to Quantum Computation Simplified. This is part 11.1 Quantum Quantum Computer for Machine Learning. So you are aware that there are many techniques available for machine learning. One of them is support vector machine. So in this video, we'll be seeing quantum support vector machine. I'm Kadiration. So why quantum machine learning when there are so many machine learning techniques are working very nicely in various fields? The reason is we want to improve further. Still, it needs a lot of improvement and making use of quantum computers. We all know that quantum computers can solve linear algebra problems much faster than any classical system. And qubits exhibit quantum states, many quantum states because of the superposition and leading to identify features faster. Quantum parallelism because we have seen that it will help the training the models in a much faster way. So we have seen exponential speed up happening through Fourier transforms, finding eigenvalues, eigenvectors, solving linear equations. So all those methods can be used in least square fitting, gradient descent method, PCA, principal component analysis, SVM, etc., which are all part of machine learning. So that's the reason actually I wanted to share this video, that there's going to be tremendous advantage in machine learning, which is already a successful process or a method. So what is the current status on quantum machine learning? So like any other problem, we also have problem here because of less number of qubits and that too noisy. So solving any today practically relevant problem is still years away, but uh, that doesn't prevent researchers from academic institutes and companies like IBM, Google, and Microsoft. They're working continuously on that and coming out different algorithms, and they try to show that there is a big advantage. And once the quantum hardware, the good one with a good number of qubits, they'll be ready because all whatever work they do, they're all scalable, right? So that's the reason a lot of effort is being put on quantum machine learning. Okay. Yeah, well, most of you are aware about machine learning, but let's have a quick recap. Machine learning can be classified in different ways. This is one such ways. One of the ways given by MathWorks. Supervised learning, unsupervised learning. So under supervised learning, we have classification problems, we have regression problems, and under unsupervised learning, we have clustering problems. So I'll not go into the detail like what problem. I think most of you are familiar. If not, you will get it from any machine learning article. And for each of these problems, there are many techniques available to solve the problems. We are going to today see support vector machine. You may wonder why I am not touching a neural network. For two reasons. One, this involves very interesting mathematics. The other one, yes, I'll come back soon on neural network with a little more detail on quantum neural network. Okay. In fact, support vector can also be used for regression, but in this video we are going to do only for classification application. So there are many techniques available for quantum machine learning, even the simple whatever we have studied, Grover search. The one aspect is the right amplitude amplification, right? So that can be used for machine learning. Quantum enhanced reinforcement learning is there. Quantum annealing is can be really used. That's the best optimization solution it will give, right? So quantum sampling techniques, quantum neural networks, hidden quantum Markov models, quantum support vector machines. So this is what we are going to see in this review. and there are many platforms, many libraries are available. We don't have to break our head today. If you have a problem, classification problem, straight away without knowing anything else you can go. But this video, whatever I am saying, it will help you to understand some basics, and then you can try to build on your own. Okay, so IBM, that is what we are going to see in this video. We are going to make use of the machine learning support vector machine learn sorry AI support vector machine approach. So the functions related to that we are going to use. Google has done a very nice work combining their TensorFlow, which is a very successful classical machine learning tool, and they married quantum with that. Microsoft also has given under their Azure quantum platform a lot of machine learning libraries, functions. Penny Lane is one of the excellent websites you can go and see. They have plenty of applications and supported by Zonado, and Amazon also has joined recently. D-Wave system, we know they are the best people for optimization, so they also work on you can use their platform also for solving machine learning problems. Ironco and Honeywell, so they are also working, but I do not know whether they also give open source functions. Okay, so what is SVM? Again, some of you may be aware, you can skip that if you want, but for others, let's quickly see how SVM works. So we know that it's a supervised learning technique used for classification and regression. So it was developed by Mr. Vladimir. So in fact, he gave this concept in 80s, and later he modified along with his colleagues in AT&T Bell Laboratories in 90s. Very, very good mathematics. It's a brilliant idea. So there are some terminologies, hard and soft margins, nonlinear classification, multidimensional classification. And we will see all those derivation. We'll try to understand what are they. So first, let's start with the classification problem. So what is a classification problem? So in this, we will be given a set of data. So we have to say whether they are true or false, they are 0 or 1. I mean, if you go into the next step, if you receive a mail, whether it's a spam or not. So how do you do that? So you have to get some features from the mail in terms of some word and things like that, right? So similarly, that's what you will have features. So the x1 and the x2 are the features. So let's take another example. Suppose you have a scanned image of some cells, okay, based on the size and the gradient. You have to classify whether it's a cancer cell or not, okay. So maybe you will digitize that diameter with some number, and similarly the color gradient with some number. I'm just giving an example. So you try to classify whether it's cancer yes or cancer no. Like that we can have many examples. So initially you will be given a set of data along with the result, or along with the classification, or along with the class names or class labels. So using that, we have to fit a model, and then later when we are given the test data, we have to say, yeah, we have to give the label back. Oh, sorry, yeah, this is yes or no, something like that. So how that is done? By defining a hyperplane. So what is hyperplane? It's basically a boundary, okay? So in this case, let us say that we have this set of data which is true and this is false, for example. So we are defining one hyperplane. This is it a good hyperplane? It's not at all good one, correct? It's for two reasons. One, typically whenever we define a hyperplane, whatever data we have on one side will be true, the other side will be false. In this case, you have both true and false on one side, first problem. And first issue. The second issue is even true also is there on both sides. So this is a very bad hyperplane. What about this hyperplane, the blue one? It's good. Okay, I'll put a tick mark. The reason here you can see it has always classified all the data. Sorry, the boundary, what the hyperplane, what it has defined, has clearly segregated the true and false data, 0 and 1 data, or cancer, yes, no, something like that. Okay, is it very good? No. Then what is very good is red. I'll put double tick. Okay, the reason here is it has got a good margin. For example, when in this case, tomorrow if we get some data like this, very close, but it will say false, right? Similarly, when it gets, so we have some data like this, it will say true, which is not good. Whereas if you have a hyperplane like this, even if you get this data somewhere here, still it will classify it correctly. So that's why this is a good hyperplane. So we need to, for every classification problem, we should have a good margin. That is the word we have to remember. Okay, so for linear, this is for, we are able to have a straight line. We may not get such data always. We may get something like this. So that in that case, what shall you do? So one possible way is you increase the dimension. When we will see it later how to increase the dimension. So afterwards you will see that the data gets segregated. So we will be able to introduce a hyperplane. We will be able to separate the classes. This is another set of data, and there's another way you transform with using a function which will move the data like this. Then it's easy to separate, right? And there is another, you don't have to always do with a straight line, you can also do with a circle. So these are all the different ways of classification, and all are covered in SVM. So how it is working? So SVM constructs a hyperplane or set of hyperplanes. So when do you need a set of hyperplanes? So we have seen now yes or no kind of thing, right? But there will be cases where you need to classify, you will have multiple classes, like animal. If you are given a picture, you have to say which animal it is. It may be tiger, cat, elephant, lion, like that. So in that case you will have set of hyperplanes. So obviously, in such cases you will have more features or more data. So the problem becomes complicated. We will not be able to even visualize. Suppose if it is 10 features are there, then you cannot imagine, right? So if as long as they are in 2-dimensional, 3-dimensional, we'll be able to do. One more thing we have to remember, that when you have 2-dimensional data, you have a hyperplane of single one. And if it is 3-dimensional, you have 2-dimensional hyperplane. So always it will be having 1 dimension less. So where do we start? So we'll be starting with the given data. So we are given here x, which will contain the features. It may be any dimension, and for that set of x you have the label. For mathematical simplicity, we will define that as +1 or -1. So that will help us to understand the mathematics better. So what is our job? Our job is to find out the hyperplane. So in this picture you can see here, we have to find out the equation of this line represented by Wt, something is missing, into x minus b equal to 0. So we'll start with the hard margin problem. So hard margin problem is we will not have any data straying over. So we will be able to draw a line like this, beyond which there won't be any data. So similarly here, this is for true and this is for false. And this line is important. So that is defined by Wx minus b equal to 1. So for any data, it will be more than 1. Similarly here, this equation is -1. And for any other data, it will be less than -1. So that is what is given here. So for y equal to 1, that is true case, it is all the data can be represented like this. Similarly, for this false case, we will have this equation or inequality has to be satisfied. So now this can be combined when you multiply on both sides with yi. So you multiply yi here. So 1 into 1, 1. So there is no change here. Whereas in this case, minus 1 is there. And again, when you multiply with y equal to minus 1, this will become plus 1. Which means these two equations become a single equation for all the values. That is good, right? So now we can write a optimization problem. So before that, let's have a look at that. So what is this width? So there is a good definition to arrive at the width is given again is a function of w only. So there is a good reference given at end of this presentation. Please have a look at that to gain more knowledge about SVM. But otherwise, you can assume that this is the width given by that. And our for a good classification, the width should be as high as possible, correct? So this has to be maximized. In order to maximize this term alone has to be minimized because it's in the denominator. So that is what is the optimization problem. So you have to minimize the norm of W without violating the constraint. So what is constraint? Constraint is this equation. So you have to meet this while minimizing that. So how do you do that? So this is same as what I have written in the previous slide. So for such a problem, optimization problem, there is something called Lagrange multiplier. And they bring in another variable. Why they do all those things is they are trying to combine both. Because now they are standing apart. So that will help us to, because once you have one equation, it becomes easy to solve, right? So this is another technique. I'm not going into the detail because you will see this video. And once you have this now optimization problem, if you typically what you do, you try to differentiate. For when you are trying to maximize or minimize, you have to equate it to 0, correct? So that exactly will be doing it. And there is something called KKT condition. So there are 3 mathematicians who have found that by doing a partial derivative, because we have 2 variables, W and B, and then simplifying it, you will get W like this. But the most important thing is this condition. This is what really makes this technique SVM a great successful one. So what does it say? The alpha into this should be equal to 0. So how does it help? You can see here the points lying here on this, in this case 2 points. So any point lying on this line, this can be met, this condition will be met, correct? That is what is given here. So when you bring it -1 this side, you will become 0. So similarly, in the other case, so alpha is 0, is non-zero because this is already 0. So alpha has to be non-zero for this these points. So and for all other points, alpha will be 0 because they are non-zero, right? So this expression is non-zero for these points, and this expression is 0 only for those points which are lying on this line, which means out of thousands of data, only few points alpha will have value, and only for those points W also will have some value. Remaining places it becomes 0. So a huge problem is simplified to few points. That's why it's called support vectors. So the points which are lying, the vector representing those points are the support vectors. They are the pillars. Remaining are all no use at all. Sorry. Yeah, so that's how this thing has become very popular. And there is one more thing which makes this popular is the kernel trick. so which really converts complicated non-linear total system to become linear or to become classifiable thing, right, by increasing the dimensions. So these two methods or processes are they make the SVM very efficient and popular. So very nicely explained the steps involved in this video. Okay. Soft margin. So we have seen hard margin. So the difference is we may have some points stray over, come on the other side. So here you can see one point has come this side. Similarly, this point has come, and just because one or two points we don't have to go for nonlinear classification, we can do linear classification. But then how do we handle that? We can handle that by defining some term called accuracy, right? Eta, we call this a slack parameter. So the problem will be similar, except that we will have one more term, the minimization problem, as well as in the constraint also we will add one more term like this. So otherwise the problem remains the same. So nonlinear classification. So how do we do that? We have seen earlier the data can be in any size, shape, it can be scattered in any way, correct? So in this case, if you see here, we cannot do linear. So we are trying to introduce another space by or another dimension called z equal to x square plus y square, where you making use of the same data. So this is x, y. We are just introducing another one. Just by doing that, we will be surprised that this set of data is getting segregated, right? Now we will be able to introduce a hyperplane. Very nice, right? So thanks to Vladimir, we are able to classify problems like doing magic. Okay, now later once you do this, later you will verify it in a two-dimensional plane. So this, you can see here, the support vectors will be lying like this. Of course, this is not for this set of data. This is totally for a different set of data. But for nonlinear classification also, you will have few data only will act like support vectors, and we don't have to worry about the remaining data. So that's all about SVM, and now we'll see quantum SVM. So we know, we have seen earlier, but again we'll reiterate, the quantum advantage can be obtained. We know that because of the mathematical operations involved, particularly to find out the hyperplane parameters, that is W. And that is initially from the trained data we need to estimate, and later we'll be using it for test data to classify. So under those two circumstances, we can make a big advantage in terms of speed. So how good it is? So that is given by SVM complexity, which is proportional to polynomial in NM, whereas QSVM complexity is given as log NM. So what is NM? N is the number of dimensions. M is the number of training data. You can see a good speed up which will happen. In fact, somebody has, again, it depends on the size of the problem, and there are many more things, but this is roughly the way you can compare the complexity of classical and quantum SVMs. So I don't know what problem they used, but they have given the result. They used quantum SVM. First they ran it in computer, mostly they would have run it in a simulator, then computer. And they also verified in a classical way using ordinary CPU. So you can see here this gives the best result in terms of accuracy and in terms of speed. So, and research, you know, that is going on quantum computer, so that they will be soon matching this. But currently classical SVM is better than quantum computer, but not compared to the simulator. So the approach, it is same as classical SVM. Actually, there is nothing like new quantum algorithm for doing classification. So this is exactly same. In fact, most of the machine learning problems, they just follow, except I don't know, maybe few people will be doing research on totally new algorithms, for example neural network or any other way. Otherwise the steps involved are same. And importantly, in this case, actually, we'll be using quantum computer for two purposes. One for computing the quantum kernel, and another time to predict. But the classical optimization, the constraint optimization, we will be doing by classical way only. There you don't get benefit. We also need to convert the data from classical way into quantum state. So you need a function to do that. So which anyway we'll be seeing it in the subsequent slide. So what we do typically, we will be given a set of training input and the test input for which we need to predict the label. So all are given to quantum device, which will find out the kernel. Using that, it will arrive at a model, and using the model and the input data, we will be predicting the label or the class. So as I told you, the approach is similar, and first we need to map the given set, the x vectors to quantum states. So that is done by something called feature map. So typically we always start with the zero state, right? And then we'll be doing some function. People call it as encoding, and some people combine the encoding process with kernel and all. But as you know that there are different ways of encoding the data, and IBM uses something called ZZ feature map, which is nothing but taking the zero state, you apply Hadamard gate, then you make use of the input data. You can see here, x0, x1, x2, like that, and the number of qubits depend on the number of dimensions. Okay, then it has got couple of control NOT gate, and depending on the size of the problem, you will do it once or twice. So fundamentally, you will transfer, make use of the given data, apply on the state of qubits to represent the data. So how that is arrived at, I'm not going to touch it, maybe in the later video. But again, you don't have to worry, because IBM has got a ready-made function which does the translation quickly. Similarly, the kernel, they have given another function which will do the kernel, and simplest kernel and easily understandable is inner product of two inputs. As you can see here, the matrix multiple, if the matrix size is more, then you need a lot of time in a classical way, whereas that can be done, the dot products can be obtained very easily in quantum way. And some rare cases you may use a different kernel like Gaussian, sigmoid, tanh, and all. Classical optimization technique is used, and then from the model you do quantum prediction. So in a block diagram way we can represent things like that. So you'll start with the zero state, you apply the feature map which will convert to 2, and while applying you will make use of the given classical data. So with that you will try to do the variational circuit. So this again will have a lot of rotational gates. So basically how much to be rotated, that's what you'll be working on it. It's called variational because this value you will keep changing till you get satisfactory result from the training data. So you will make a measurement, then you will define a function to convert this measurement to the +1 or -1 value. Again, we know that they are all probabilistic values, so we may have to run many times to know the probability of the right class, what we get. So there is something which is going on inside that is explained here. So from W, you take the output like what you are seeing, whether that has met the objective. If not, you change the value, and you will be doing this number of times until you get the satisfactory result. So this is what is being done in IBM in one of the functions which we'll be using. So you will have a very detailed one in this page, but I'm not going to run in IBM server. I copied whatever functions they are given. I copied only the relevant one, and I'm going to run it in my computer. So as you can see here, I mean this is not, I mean it's purely IBM code. We have to import certain functions what is required. What you see here specifically, there are, I mean this is the, these two classes are, I mean new for general, we have never used, correct? So what it does, you can see here, basically depending on the feature dimensions and how many times you want to repeat to get that, whether you can afford an entanglement or not. So based on that, it will generate automatically the circuit required. So really we don't have to break our head. Similarly, the SVM function will do all the three things which we want to do. Training or estimating the W, the weight matrix, optimization, and then predicting the value. So everything is done by QSVM. You can see here QSVM. So given the feature map, training data set, and then whether it is binary class or a multi-class, accordingly it will use those functions. Okay, and once you run it, okay, maybe you will see here. All right, shall we run it? Okay, so sometimes, okay, one more thing I want to tell you, that now they moved all these libraries from Aqua to Terra. So when you run it in IBM example, you may see some warning message, deprecation and things like that. So you don't have to worry, you run again, or possibly they are also given like where it is available, where you can modify it. Okay, so after importing, we are trying to get some data, ad hoc data, which is again available in their library. And then from there, you take something random sample, you do it. That's what you are trying to do here. And you are defining what is the training size, what is the test size, and things like that. And we are also plotting the data, what is available. I'll run it. It's running. May take a couple of seconds more. It's taking time today a little longer. Yeah, so this is the data. Obviously this is not linear, we have to do some non-linear. So we can say either A or B. I mean A is blue or 0, like that. So here this is what we are going to do. So we have seen feature dimension, we have given us 2 repetition, the size of the circuit. Entanglement, we are seeing okay. QSVM, we are calling this function with all this data. We are giving some additional, apart from testing, we are also interested to do some other test points. That is what we are going to do now. Then you create an instance with where you want to run, either in the simulator or any other hardware, and define number of slots, and then what kind of random simulation you want to do. All those things you define. Afterwards, let us run it. So I'm going to print the expected value and the predicted value. And luckily you can see here there are a lot of features available. In the result you can get the model, and then you can apply with a different set. You don't have to run every time all these things. You can use those instance. You can see here this is the expected value and the predict value are absolutely matching, and then success rate is 100. What else we want? And in order to get a feel of how it compares with the classical learning, so that also has been given by them, and of course that runs quickly for this example. You can see here the success rate is only 55%. So quantum SVM is not only expected to be faster. Now it's not faster, but it's very, very accurate, correct? All right, I know that I'm not, I mean, we have oversimplified, but we can go to the more detail. But as you can see here with just two functions, even if you don't know, you can do any classification problem with these two functions, what you see here. Or, but of course, there are some drawbacks for other types. I don't know whether it will work efficiently or not. We should have some freedom to do different type of mapping. Similarly, we want to have different types of we want to try out different types of optimization problems and things like that, which is not possible to the best of my knowledge. So hopefully IBM may come out with a different thing, or you can do it. But in order to do that, we need to understand a little more than what we have seen today. Let's go back. And these references will help you, will help us to do that. In fact, as I told you, excellent explanation of each step involved in SVM is given here. And Wikipedia is always the source of information for any topic, right? And another thing which I noticed was the Quora, Stack Exchange, Jigwag. I mean, there are very nice questions asked, and some people have given an excellent answer, so that will help you to understand. Because actually, frankly, when I started, I didn't have any knowledge about SVM or QSVM. But today I'm able to talk little, and I don't say I'm an expert, but certainly all these references have helped. Possibly if I again iterate once or twice, maybe I can come out with my own coding. Similarly for quantum SVM, again wiki plus there are many papers available. You can see there are plenty of papers available. Everybody is trying to do in a slightly different way, and then trying to explain, trying to focus on certain aspects. So they're all nicely given here. I hope you enjoyed, and then what else you can do? I mean, you can explore the IBM library further, or you write your own methods. So once you get hold of the steps involved, you can try out with different set of data and use the same library or your methods. And then you can also try out other open source platforms like Google and Microsoft. And you can extend to other ML algorithms, right, like neural network. That's what I'm going to do. I'll study, and then maybe in the next video we'll go into a little more deeper into the subject. So till then, bye. Thank you for watching.